This presentation is the pre-lab discussion for experiment number 8, the final experiment of the semester, entitled Electrochemistry, Voltaic Cells. In this particular experiment, we'll find ourselves examining redox chemistries, and we'll also be constructing voltaic cells. Measurements of the cell potential being made for each of the voltaic cells constructed. If that weren't enough, we'll also find ourselves using the Nernst equation so as to determine the concentration of copper in an unknown solution. Now, I know what you're thinking. That capital N in Nernst is there because it's named after an individual. You would be right. This, of course, is not Nernst. This is Nernst. Now, before you look at this image and tell yourself, boy, that's one attractive individual, hold the Michael Myers. Is he not equally attractive? Our redox chemistries occur because we have both oxidation and reduction occurring. These redox reactions clearly are going to involve the transfer of electrons from one species to another. And as you would have seen in a previous class, it's possible to write these redox reactions to separate half reactions. One half reaction, termed oxidation, sees the loss of electrons. That is, electrons are produced, given up, donated, if you will, so as to allow a second half reaction, known as reduction, to occur. Just as oxidation represents the loss of electrons, reduction represents the gain. We consider as an example the oxidation of zinc, followed by perhaps the reduction of copper. Zinc undergoes oxidation by giving up 2 electrons, which are then given to copper 2, so as to see the formation of copper metal. Combine these half reactions, the electrons cancel, and I'm left with the net, that is the overall redox equation, which has again the oxidation of zinc with the reduction of copper 2. Each of the half reactions in that previous slide has associated with it a standard potential, represented by the symbol E0, and have in units of volts. These half reactions, again, have potentials associated with them, and they're almost always given to us as reduction reactions. That is, if I go to the textbook, I'll find the reduction reaction for copper 2 and the reduction reaction of zinc 2. With each of the 2 reduction reactions, I have standard reduction potentials. Positive 0.34 volts for copper 2, negative 0.76 volts for zinc 2. Now, in this experiment, we're going to construct voltaic cells, also known, by the way, as galvanic cells. These cells rely on a spontaneous redox reaction to produce electric. We will always find ourselves separating these reactions in different compartments so as to force the electrons or current through some external circuit. Here is an example of what a galvanic cell, a voltaic cell, might look like. I have my 2 compartments, that is the beakers, which contain the metals or electrodes, and the aqueous solutions. I have zinc metal and a zinc solution on the left, copper metal and a copper solution on the right. And between the 2, I have a U-tube containing an aqueous salt solution, representing my salt bridge. Let's take a closer look at this. I have 2 compartments, a compartment on the left and a compartment on the right. On the left, I have my zinc electrode. On the right, I have my copper electrode. Each electrode is immersed in a solution, a 1 molar solution of each of the 2 metals. I expect the zinc to undergo oxidation. It'll produce electrons which travel through a wire so as to give rise to the reduction of the copper tube onto the copper electrode. That is, with time, the zinc electrode gets smaller in mass and the copper electrode gets larger in mass. The electrons traveling left to right would cause the immediate cessation of the device. That is, everything would stop damn near instantaneously, if not for the inclusion of the salt bridge. The salt bridge allows for the motion of ions, preventing charge buildup as the electrons travel left to right. Anions travel towards the anode, cations travel towards the cathode. Generally, between these electrodes, I'll have placed a voltmeter so as to measure voltage. For this particular electrochemical cell, at standard conditions, I expect a voltage of 1.10 volts. Looking at the voltmeter in the actual picture, it reads 0.006 volts, which tells me this cell in the picture, not yet complete. Moving on. If one wants to calculate the potential of an electrochemical cell, that is your Voltaic cell for standard conditions, we use standard reduction potentials. And of course the equation which appears on the screen. By taking the difference of the standard reduction potentials, it's possible to calculate the standard cell potential. I take the potential I find from my cathode and I subtract from that the standard reduction potential for the anode. Here, the standard reduction potential for copper, my cathode, is a positive 0.34 volts. And I'll subtract from that the standard reduction potential for the anode produced from zinc, a negative 0.76 volts, giving rise to a positive 1.10 volts. This, of course, represents the potential for standard conditions. For non-standard conditions, where concentrations are anything but 1, we find ourselves using the Nernst equation. The Nernst equation would allow us to calculate the non-standard cell potential by subtracting from the standard cell potential a correction factor of sorts. R, our gas constant, T, our temperature, N is the moles of electrons transferred, F, Faraday's constant, and Q, the reaction quotient. Now, for this particular experiment, we'll find ourselves working with non-standard conditions and determining the concentration in an unknown copper-2 solution. For this part of the experiment, that is part 3, the concentration of zinc will be 1 molarity. With that known, we can rearrange the Nernst equation into the form which appears on the screen. The non-standard cell potential, which we'll measure, will be equal to 0.0257 volts divided by 2, the 2 being the electrons transferred, multiplied by the natural log of the copper-2 concentration, and add into that the standard potential, 1.10 volts. I know what you're thinking. This particular equation looks a lot like the standard equation for a line, y equals mx plus b, and you would be right. That said, a plot of the non-standard potential, that is the y-axis, versus the natural log of the concentration of copper-2 on our axis will be linear. Consider the following plot. Again, I have the non-standard potential on the y-axis versus the natural log of concentration of copper-2 on the x-axis. The slope, 0.0132, is very close to the 0.0257 divided by 2. And the intercept, 1.059, fairly close to the expected value, 1.10 volts. Given this particular equation, it's possible to calculate the concentration of an unknown copper-2 solution. That, of course, is what we'll find ourselves doing in part 3 of the experiment. You measure the potential for an unknown solution that represents your value y, and you solve for the concentration, which will be your value x. Let's consider the experiment as a whole. In part 1 of the experiment, you're going to examine different mixtures of metals and salt solutions. You're going to look for evidence of a redox reaction. That evidence might involve the evolution of a gas, the deposition of a metal, or even the formation of a precipitate. Or there won't be any evidence at all, in which case you might write as your observation, no reaction. In part 2 of the experiment, you're going to construct several voltaic cells using a 24 well plate. It'll be really straightforward. We'll be adding solutions to various wells on the well plate. We'll wet a piece of filter paper and use it as a salt bridge between two wells. And then we'll measure the potential between the two wells. In part 3 of the experiment, we'll construct several voltaic cells from zinc and copper, again using a well plate. However, here the concentration of zinc 2 will be kept constant at 1 molarity, while the concentration of copper 2 is varied. We'll then construct a Nernst plot so as to find the concentration of copper 2 in an unknown solution. Consider the following example. Imagine we produce the plot which appears on 2 slides before. We then measure the potential between a zinc cell and an unknown copper 2 cell as 0.89 volts. We take the equation from the Nernst plot that we produced, and we again for y, the measured potential. We then solve for x. X represents the natural log of the copper 2 solution. So once I do solve for x, I apply the inverse natural log, that is E, to obtain the copper 2 solution of 2.8 times 10 to the minus 6 molarity. And that, of course, is what we'll be looking at in part 3 of the experiment. I know you're thinking, God, is that all? Yes. This is what the experiment is all about, and I think you've got a handle on it. I hope you all have fun. We'll see you soon. Enjoy.